Everyone, thank you for joining us for our webinar today. My name is Samantha Donalds. I'm the Communications Manager at the Clean Energy States Alliance, and our webinar today is Energy Storage in Chattanooga, Tennessee, Creating Community Resilience and Peak Demand Reduction with EPB. We've got a really exciting roster of speakers lined up today. I should also mention this webinar is presented by the Energy Storage Technology Advancement Partnership, STAP, which is a collaboration between the U.S. Department of Energy Office of Electricity, Sandia National Laboratories, and the Clean Energy States Alliance, CESA. We will tell you more about all of that in just a moment and introduce our exciting speaker lineup. Before we do that, I'd like to go over a few very quick webinar logistics. All of our attendees are in listen-only mode. You've got a couple of options to join the audio portion of the webinar, telephone or computer audio. If you'd like to minimize the webinar console to view the presentation full screen, you can click on the orange arrow that you see circled here, and you can also click on that orange arrow to expand your webinar console. One thing you may like to do with your webinar console is submit your questions and your comments. We will be saving at least 15 minutes at the end of our presentations for a Q&A with the audience. We'll get to as many questions as we can. Make sure that we get to yours by typing your questions in as soon as you think of them. And a final note from me, we are recording today's webinar. We'll be posting a copy of the recording and a PDF of the slides today or tomorrow. We'll put those on CESA's website at cesa.org/webinars. That is a great URL to know because it is where all of our upcoming and archived webinars live. So with that, I am pleased to pass it over to my colleague who will be moderating this webinar, Todd Owinski-Paul. Todd is a Senior Project Director here at CESA.
Thank you, and welcome to this webinar. This is, I think, going to be the last STAP webinar of the year, I believe, unless we sneak one in at the last minute in December. So if you're not familiar, I will be giving a very brief introduction as to what STAP is and does, but before I do that, I will give a very brief introduction as to what CESA is and does. And then we will go right into the presentations. So if you're not familiar with CESA, Clean Energy States Alliance, we are now celebrating 20 years working with states on clean energy policy and program development and demonstration projects and research and all sorts of things. And essentially CESA is a membership agency for those state energy departments that are engaged in all sorts of programs, and these are some of our members you can see on this slide. Go ahead to the next slide, please. Among other things, we have a long-standing relationship with Sandia National Laboratories and US DOE Office of Electricity to help with this Energy Storage Technology Advancement Partnership, STAP project. This is something that we've been doing for over a decade now, and essentially there are three components. One is to help bring states and utilities and industry partners to the table, along with Sandia and DOE, to jointly support energy storage demonstration projects. And these projects have been done all over the country. There's a picture here of a ribbon cutting from a project that was one of the recent ones. I believe this was about a year ago in Albuquerque, New Mexico. Second thing that we do is to support state energy storage efforts with policy and program development assistance and technical support. And the third thing is to disseminate information, and that includes these STAP webinars as well as other things that we do. Next slide, please. So I want to thank Dr. Marie Juk, who is here with us today, and Waylon Clark, who's also here with us today, from DOE and Sandia, respectively. And without their support, none of this would be happening. Next slide, please. So today's speakers, we're going to get an introduction from Dr. Juk, again from DOE Office of Electricity. And we will then hear from Jim Glass, Senior Manager of Smart Grid Development at EPB in Chattanooga, Tennessee, and Aaron Willey, a planning engineer for Smart Grid Development, also at EPB. Waylon Clark from Sandia is here for questions and discussion. And I am your moderator. And I will just say that if you have questions, if things occur to you as you're watching the presentation, please type those into the question panel, and we will get to as many of those as we can after the presentations are over. So if we could go ahead and bring up our speakers for today. One other thing I want to mention while we're doing that, I gave very brief intros. Full bios are in the chat. So if you wanted to download, there's a handout. If you want to see where everybody went to school and what they majored in and so forth, please feel free to download that bio document. Okay, so with that, I will turn it over to Dr. Zook.
Hello, everyone. And I'm Imre Duke, and I'm Chief Scientist at the Department of Energy, Office of Electricity. And well, imagine a bright summer day in Tennessee. We have a little place for it, reserved, a platform. We have people sitting there waiting for the ribbon cutting, and it's a really cheerful event. And everybody is there. We have the mayor of Chattanooga. We have several state and federal Congress folk. We have, I think, the fire chief, and well, just a wide variety of people, all of them celebrating this wonderful box that's sitting there, the energy storage. And we cut the ribbon and shook hands, and there it was. And then sometime later, it didn't work. These things happen. In fact, it almost exploded. So this is not one of the projects that was immediately successful. However, since we were involved in it, we decided we were going to make good on our promise, and we introduced a different technology, lithium ion, and we arranged for the construction of a new energy storage project in Chattanooga, Tennessee. And you will now hear how that worked out, and Jim will be telling it to you. Jim?
All right. Thank you, Dr. Zook. Let's see. Share the screen here. All right. I think we're ready to roll. Good afternoon, everyone. I'll give you a little bit of maybe some background, first of all, on EPB. We are a municipal utility here in Chattanooga, Tennessee. We serve about 190,000 homes and businesses with electric service. We're the distribution company in Chattanooga. We buy all of our power from TVA, and then we distribute it around Chattanooga. The other thing that we do here is we are actually a telecommunications company as well, and we offer fiber optic service in the form of internet, TV, and phone. Make that available for all of our customers as well. Back in 2010, we were the first company to offer gigabit per second internet service in the United States, and picked up the name Gig City because of that. And more recently, we've now been able to offer up to 25 gigabit per second internet. So fast internet here in Chattanooga, and we take advantage of that for all of our smart grid technologies as well. What I wanted to try to cover with you all today is a little bit about how we got started in energy storage, and then go through some of the use cases of why we're using it. I'll talk a little bit about each of our projects, and then we can go into kind of where we're headed next. Back in 2010, 11, and 12, EPB installed about 1,200 automated switches on our 12 kV distribution system. And this is a schematic of a typical feeder. The substation breaker is over on the far left side, and each of the red boxes that you see there are normally closed switches, and each of the green squares are normally open switches that tie to other feeders. And the way the distribution automation technology works is that if we have a fault, say in between two switches, the switch upstream would recognize the fault, open to interrupt the fault. It would communicate with the switch downstream to open so that they've got it isolated, and then they would communicate with another open switch that could close to restore power kind of on the back half of the circuit. Well, that technology did exactly what we needed it to do. It improved our reliability dramatically. We saw more than a 50% improvement in customer minutes of interruption every year. And the thing that we didn't realize at the time was that it also set us up for a new technology or a new approach to our distribution system called microgrids. And we average about 750 kW between switches of peak load, and about 150 customers between switches. And that was a good size for us to be able to consider something like a microgrid. We communicate with all the switches using the fiber optic network. And so after we had kind of been working through some of this, we were approached by a professor at University of Tennessee who understood a little bit about what our automation technology was capable of, and he asked us about partnering with him on a project to develop a microgrid in Chattanooga. And what we decided to do was take advantage of about 2.5 megawatts of solar PV that had been installed by the Chattanooga Airport, and it's interconnected directly to our distribution system. So we applied for a grant from ARPA-E and were successful in receiving that. And what we did as part of that project was we installed 2 battery systems. They're also interconnected directly into our distribution system. We're able to control these through SCADA. And what we were able to do as part of the project was create a microgrid capability in this area. And just to kind of show everybody what's installed, down here at the bottom right of this display is where we have our battery interconnected. The solar PV is interconnected, and then we also installed a natural gas generator. And as you can see on this feeder, there are actually a lot of ties to other circuits. And so this is kind of in the middle of town. It's has a lot of redundant options from other feeders. However, if there was a case where none of these options were available, what we can do now is we could actually open this switch so that we're completely isolated from the traditional grid. We can start up the battery to form the grid, and then the solar PV can be used to supplement that. And one of the unique features about this microgrid is that it's able to manage what we call flexible boundaries. And what that means is that if there is a large amount of solar PV generation available, we can actually expand the boundary out another switch or maybe one more and serve more customers. And then if, that evening, if when the sun goes down, if we're still operating in this island mode, we can collapse the boundaries back down to a smaller area that would be served only by the battery and the generator. So that was our first experience with energy storage and our first experience with a microgrid. We learned a lot from that project, and what we did from there was just kind of recognize what else we could do with energy storage. And so we developed kind of two primary use cases initially, and then I'll talk about a third one here in a second. But the first thing is simply resiliency, that utilizing the automated switch infrastructure that we had, we recognized that with storage and or possibly other DER assets, we could provide a kind of a redundant power option for critical facilities like at the airport. And this is the equipment that is served by that microgrid is not the airport terminal itself, but there is some critical FAA equipment that is served in that area, and that's what we're able to provide redundancy for. There's another case where we have some radial circuits, and I'll show you an example of that in a minute, but it's feeders that really don't tie to another 12 kV circuit, and we're working on a couple of projects now to provide an alternative source for those feeders. The other thing that we use batteries for is demand savings. We are on a wholesale demand and energy rate from TVA, and I've listed our demand charge that we pay every month on there. And so by using the batteries to shave our peak every month, we can save a lot of money, and it helps to pay for the batteries themselves, and has worked out very well for us. And then finally is kind of a special case of demand savings. Back in December of 2022, TVA had, for the first time in its 80-year history, called for a reduction of load from all of its local power companies. And on December 23rd, all of the local power companies were asked to reduce their peak by 5%. And what that meant for most of the power companies was that they actually had to rotate feeders. It was the first time that had ever been done in TVA's history. What we were able to do was utilize the energy storage and also some other projects. We've got the capability to reduce our peak through voltage reduction, and then we also have some programs with some large commercial and industrial customers that we were able to curtail. And so on the 23rd, when many of the local power companies in Tennessee had to rotate feeders, we did not. And the energy storage was a big part of the reason for that. The next day, TVA came back and said, we're still in this event, and now we need you to reduce by 10%. And we weren't able to achieve all of that with the demand reduction technology, so we did end up having to reduce or having to rotate feeders a little bit on the second day. And I hope we never have to do it again. But the energy storage was a big benefit for us and enabled us to avoid that on the 23rd. So I want to move into a couple of the other projects that we have been working on. This is an aerial shot of our control center campus, and we implemented a community solar project here at this site about 5 years ago. You can see all the solar panels there. And what we did as part of this project was to add energy storage, and we're essentially doing something very similar to what we did at the airport, where we can, if the need arises where our traditional sources of power are not available, we can isolate this campus using the automated switches, and we can run this campus off of the battery and the solar PV. We would initially would open switch 1, switch 2 is already open, and then we can start up the battery and utilize the solar to supplement that, and depending on the load situation can go a little bit further back towards the substation and pick up some additional load. This is a photograph, or a couple of photographs of the battery that's installed here on our campus. It's a 1.2 megawatts, 2.5 megawatt hours. It's a Tesla Mega Pack. We commissioned this one last April, and this is the one that Dr. Juk was talking about, where we partnered with the Department of Energy and with Sandia National Labs on this project. On the right, you can see the Mega Pack in the background. On the right side is the step-up transformer, and on the far left is our communications and control equipment, and then the taller cabinet on the left is just a disconnect switch if we need to isolate the battery from the transformer. Going back to our use cases, for this project specifically, we're able to save about a little over $100,000 a year on our demand charge, and the net present value calculations for this one worked out pretty well for us. And then the microgrid capability that I described a little while ago, it offers a kind of about a third or fourth level of redundancy for our control center campus. And also, this was one of the batteries that we were able to use for reducing our demand when TVA had its capacity shortfall event. All right, talk a little bit about another project that we worked on, and this one was for the City of Chattanooga Police Headquarters. They have a campus here in Chattanooga with one large building and several smaller buildings, and we really took the same basic approach. Down at the bottom, there are a couple of switches. The red one is the normal source of power into this campus. The green one is an open point to another circuit. So we have alternate feeds that can come into the campus. However, if both sources are not available for any reason, we can open up this switch and start up the battery to provide the voltage and the frequency source. Then the solar PV, which in this case is actually owned by the police department, it's on their roof. It can be used to provide power. And again, in this one, we've got another generator that's available to supplement the battery and the solar. It's really designed only to provide power, really, if we don't have any sunshine for a couple of days. The solar and the battery can typically provide power, but if we should go a day or two without any sunshine, we could use the generator to supply power for the entire campus. And this one was commissioned last fall and has been available since then. Just a couple of photographs, or a photograph. This is the battery on the far right. This is the generator that was installed at the site. The battery is a 500 kW, and is able to support the site for probably about 4 or 5 hours. Their peak load is a little over 200 kW, but they don't get up that high that often. So so we can run the site off of the battery and the solar for the most part. All right. This is the last battery project I was going to talk to you about. This one was not set up to be a microgrid. This was a site that we developed primarily for demand reduction. And in this case, we've got 3 megapacks that are installed here, 3 disconnect switches and 3 transformers over here. And so the total capacity is 4 megawatts, 8 megawatt hours. And for demand reduction purposes, our peak typically lasts for about 2 hours. And so that's why we've got it sized this way, that it can carry us through a typical peak event and reduce that demand by 4 megawatts, which using the current TVA rates is about $45,000 a month that we can get a payback on from this system. So those are the systems that we have installed that are all operational today. This is a project that we are currently working on. It's another resiliency or reliability project. This is at the very far north end of our service territory. The Tennessee River is over here on the right side of the picture, and to the north is the end of the world as far as we're concerned. And this is about, just to kind of give you some idea of the scope, this is about 7 or 8 miles from the left all the way out to the river. And so we've got several of the automated switches along this route. And you know, today what would happen is if we had a tree fall somewhere here in the middle, everybody beyond that point is out of power. And we're not able to provide a redundant source for this feeder because we've got the river on the east side, and we actually don't serve the other side of the river. And then if we tried to build a tie up here to the north, it would be probably 12 or 15 miles that we would have to build a circuit. So it's very, very difficult to do something that big through a lot of farmland for the most part. So what we have chosen to do is we purchased property. We actually closed on the property last month, and are planning to install a battery system out at the end of the feeder, so that if we have a fault somewhere upstream, we can isolate the fault and use the battery system to provide power for the customers beyond that point. And that's the next project we've got in the works. The battery has already been purchased, and we're starting the battery site development now that we own the property. Quick summary of kind of what we just talked about. All the ones that are currently in service add up to a little over 6 megawatts of capacity. The battery projects that we currently have in progress is about another 6 megawatts. That first one is the one I described up in, it's called Sail Creek. We're doing a very similar project not too far from there, another kind of a remote area that does not have ties to other feeders. And then finally, there's one at a construction trade school here in Chattanooga. This is a site that has been created to train craftsmen in plumbing, electrical, construction trades, and it's a community partnership that set up the school. And so working with them, we are installing a battery there, and we'll be putting some solar PV at the site. and creating another campus microgrid. So what's next? Well, we are in the process right now of finalizing our selection of a battery partner, really, to purchase about 4 battery systems a year over the next 5 years. So we're planning to install a lot of batteries. The use cases for these are just what I talked about before. There's the resiliency projects where we've got radial feeder sections that that we want to install battery systems out at the edge and provide that alternative power supply. The other thing is strictly for demand reduction. We've got about 16 substation sites that are now vacant. They're older, small substation areas that are no longer in service, and we can utilize those for energy storage projects. We've already got the infrastructure in place and are planning to take advantage of some of those. And then last but not least, we were very fortunate last month. We were selected to be the recipient of one of the GRIP grants. We submitted a proposal to improve resiliency in our area, and part of that proposal included 6 microgrids. So 6 of the 13 resiliency projects will be part of that GRIP funding, and we just started working through all the negotiations and so forth with the Department of Energy on that, but are looking forward to getting started with that. So I think that is it as far as the presentation content. And if you all have questions, Aaron and I can take a shot at trying to answer those.
Thanks very much. Please come and turn your cameras on, all the presenters, and we will get to the questions. Very interesting series of projects here in Chattanooga. Dr. Zook, if you're still with us, and Waylon, if you're still with us, turn your cameras on and join us. So we do have some questions. One person is asking, does the TVA long-term contract affect local power companies' ability to install battery energy storage systems?
Good question. No, it doesn't. The long-term contracts that we now have with TVA, they allow for about 5% of our power to be either self-generated or purchased from somebody other than TVA, but energy storage does not count against that cap. The assumption is that we would be charging those batteries with TVA power, so we're not actually, generating any power from a different source.
Okay. Are there non-EPB batteries or storage assets in the service area? And if so, how do you interact with those?
There are not any that I'm aware of. We definitely don't have any batteries that are directly interconnected to our distribution system. Aaron, are you aware of any batteries behind the meter anywhere?
Not commercially or industrially, but residential, installations are becoming more and more broad with the installation of solar. But as far as like Tesla power walls and stuff like that, but not any utility scale energy storage systems.
Okay. Somebody wants to know how long you would allocate for an average project from start to interconnection.
Let's see. Kind of depends on the nature of it. I mentioned that in some cases we're using vacant substations. Those can go a lot faster because there's not a property purchase that has to be done. We already own the property. It's just a matter of going in and preparing the site and then obviously purchasing the battery. I would say though, in general, it's probably maybe a 2-year lead time. When you add in the lead time of the battery purchase, if you have to do any kind of property purchase, that adds time and certainly the site prep. But I would say from maybe the day you decide to do it to when it's commissioned, it's probably in that, and again, depending on whether or not you've already got the property, maybe 1.5 to 2 years.
Hey, Jim, I think
Friends from Sandia and DOE may want to chime in on this. I know we've seen some fast ones and some delayed ones over the years.
yeah, and I think it'd be interesting, Jim, if you told the story about the what happened with the community microgrid battery when that Tesla battery showed up. That there are one-off delays that you won't always experience, but I think it's worth recognizing that some things can happen.
Yeah, there's the battery that we installed here at our campus. The first one that showed up looked like it had rolled off of the truck. So Aaron wouldn't accept it. It was kind of beat up, and when Aaron met the driver that day, he said, we can't take this, and we called Tesla, and they said the same thing, don't take it. So that created a little bit of a delay. To be honest, though, that one, in that specific case, it wasn't that long. It was a few weeks. But Aaron, do you remember how many weeks it was till the new battery showed up?
It was less than a month. It was no more than 4 weeks.
Yeah. So, but that is a good example of just what can happen. There had been something happened during the delivery process, not sure what, and so we had to wait on a new battery. The other thing I'll say, and the reason I mentioned that about the property purchase is, creating a battery site is not too different from trying to create a substation site. Nobody wants it in their backyard, and so we had identified one site initially for the battery up in Sail Creek, very remote location, and several of the customers were not happy about the spot that we had picked out, and so we ended up finding a new spot about 1/4 mile down the road that worked just fine electrically, but we were able to kind of hide the site from view a little bit better, and that seemed to please the customers, and so that's where we're going forward with the project.
Great. So if somebody offers to sell you a battery that fell off the truck, you
Yeah, I would advise against that.
Okay. A couple of people are asking about the expected lifespan of these batteries, and also what the end of life disposal plan is for them.
Okay. Talk about maybe the lifespan first. I think there's a couple of things there. One is that in our requirements that we put out for the bids, one of the things that we included was a 10-year warranty, that not that the battery would last 10 years, but that it would meet the nameplate warranty or our desired size for the energy capacity. And so if we left the option open to the bidder about whether or not they wanted to oversize that up front, or if they wanted to replace cells that had showed some degradation. But essentially what we said is that if we are putting in a 1 megawatt, 2 megawatt hour battery, that 10 years from now, we wanted the energy capacity to still be 2 megawatt hours. And so that was one of the things that we put in to make sure that we got our 10 years worth out of it. We are seeing vendor warranties, though, that exceed that. 15 years for our most recent bids that we just received. One of the vendors goes out to 15 years on their warranty. So we're planning on 15 plus. You know, I'd like to see 20, and but I think what we're seeing in terms of the financial payback, it's more like 5, 6, 7 years will ensure that we get our financial payback on it. Plus, obviously, we're getting all the reliability benefits from these as well. To address the question about what do we do with them when they're finished, that's something that's interesting. I had a meeting earlier this week with a company that actually specializes in decommissioning of solar sites and battery sites. And it's not that they necessarily take the material, but they find partners that will take the material for either repurposing it, recycling it, whatever needs to be done. And so that's kind of what I would envision. And I know Waylon or Dr. Zook, you may want to comment on this, but I think a lot of the materials in the battery cells, it may be possible to repurpose those, reuse those, and I think, you know, what I expect to happen is that there may be some new industry created around that, specifically for that purpose.
Emery, I can't hear you if you're trying to.
I was still muted.
There you go.
I'm muted now. Okay, well, that's what we're hoping for, because we do need to eventually recycle these materials. We are looking for new sources of lithium, but we are pretty much stuck with the production as it is now. And we're seriously worried that there may not be enough lithium to cover the entire market, because it'll grow and grow as we grow with solar and other renewable energies. At the moment, we really don't do that well with recycling lithium. There are companies that can do it, but generally we rely to some degree on grants and what have you. You know, but I'd really like to see companies develop that can do that. The lead acid industry has done it, and they recycle 98% of their material. And that's the kind of thing that would be nice for lithium. Not going to happen though, because a lot of stuff that simply isn't worth recycling in lithium-ion batteries. But the lithium we do want, and probably the nickel and the cobalt.
Yeah, actually, we had an STAP webinar on this topic very recently. Battery recycling and reuse, and actually we had one on lithium sourcing as well. Look in the CISA webinar archives, and you can watch those webinars. I want to follow up, Jim, on a couple of the things that you just spoke about. You sort of implied that you're getting batteries from different vendors. Are these not all from the same manufacturer?
No, not all of them have been from the same manufacturer. That's actually why we did this RFP for the next 5 years, is that we could focus on one technology or one manufacturer for this. Of the 4 battery systems that I described a while ago, they're from 3 different vendors, and it was just a matter of, you know, each one was a separate RFP process, and For each one, we were selecting the lowest bid that met our requirements, and we ended up with 3 different companies and all that. And so now what we're planning to do though is find a long-term partner so that our commissioning process, the integration with our SCADA system and so forth becomes much more consistent, and we don't have to redesign that every time we have a new battery system.
Sure. You mentioned Tesla. Can you tell us what the other battery
Sure.
makes are?
Yeah, the one at the police service center is from a company called ELM, and then the one at the airport was from NEC Energy Storage, and they are no longer in the battery business. They NEC decided to discontinue that branch of their company 3 or 4 years ago, and they're still supporting it and maintaining it, but they're just not selling any new batteries.
Okay. And then you also mentioned the payback period, and we have several people asking about this. I wanted to circle back to that. Is that based on primarily demand charge management, or are there other, are you doing any frequency regulation or any other arbitrage or anything?
Now, at this point, it's all about the demand reduction. We looked at the energy arbitrage, and there was a very, very small payback on that. Plus, it required cycling the battery many more times per month, and we were a little concerned about the degradation that might cause. And then, as far as frequency regulation, we're really not in that position. That's more of the TVA, being our G&T company. They're responsible for the frequency regulation. Now, I will say, we have in each of our battery systems, we've got the capability to use it for voltage and bar support. Every inverter is a 4-quadrant inverter, and we created that capability. Have not had to use it to this point, but the capability is there for every one of them.
Okay, and then obviously you're getting a resiliency benefit or a backup, power, however you want to term it, almost like insurance. Were you able to value that in some way when you did your, cost effectiveness analysis for these projects? Was obviously it's not something you can really monetize, but can you include it? And if so, what values did you arrive at for that?
Well, we didn't try to put a dollar figure on it. What we did though is compare it to the alternative of trying to build a feeder tie in those locations, and it is more cost effective than trying to build 12 or 15 miles worth of new feeder. So that was really what it came down to, is just a cost comparison, not trying to say that it was a cost savings or cost reduction.
Interesting. I just wanted to mention we have a similar proposal right now here in Vermont. Green Mountain Power is talking about putting batteries actually behind customer meters in some areas where they're remote, and it would cost more to, underground lines and so forth because there's frequent outages. So the cheapest remedy may be in some cases storage. So somebody is asking, after completing all of these projects, what would you say your biggest lessons learned are during the design and construction phases?
Let's see. Aaron, anything come to mind immediately for you?
Kind of the obvious one is to plan ahead. In the current supply chain, there are significant delays. So, there, as Jim mentioned, that these projects are could be up to 2 years. So you do have a lot of time to plan. But if you kind of owe the secondary equipment or any of the auxiliary equipment to support the microgrid, if those are an oversight, you're looking at least a year lead time for switch gears. So that's a lesson to be think forward on ordering equipment. The equipment sizing, as Jim mentioned, we decide, or we prefer to oversize our systems up front. So in your RFP process, specifying the end of life rating of those systems, that wording, the battery manufacturers understand that wording a little bit more than saying I want this amount of battery left, either that usable power or rated energy. End of life is a good term to specify and oversight your system on the front. But those are kind of the two lessons. There's a lot more on the construction side, but those just kind of come and go based on the tradesmen that you have and the crews that you have working, whether you're doing that on an RFP or whether you have that internal resources to be able to construct the site. But there's a lot on the actual project management side, but that's mostly what resources you have and what resources you're working with.
Aaron, when you said you brought up the construction, that made me think of something. We had to do some clarifications in our most recent bids around the construction. Some of the battery systems are all contained in one container, both the battery modules and the inverter, and others are two separate containers. And in order to make sure we were comparing apples and apples, we ended up specifying that if you had to do DC cabling between your battery cabinet and your inverter cabinet, then you're paying for that cable. And so some little things like that came up just through the RFP process. That one we were able to clarify as part of the requirement this time around. But a lot of things like that come up in the construction, and even how many devices are required, because if you've got to do conduit between the containers, things like that, generally we prepare the site with the battery pad, the concrete pads, and the conduit installation and so forth, and then we're just purchasing the batteries themselves. And so understanding about how many pads had to be poured and how much conduit had to be installed, those kind of things were important in understanding the bids as well.
Yeah,
Great, thank you. Go ahead, Aaron.
The more conduits you have, the more pads you have, the more opportunities for errors and where those conduits stub up. And it takes a lot longer to build that, so it increases the odds of a mistake. Because once you get the equipment delivered, you've got energy modules that need to be energized and can only be stored for a certain amount of time without AC voltage on it to maintain the systems. That's and I guess another point to add on the logistics, even though you may have a site for a battery, you need to look at all the surrounding environment to make sure that you have enough space to get a crane and an 18-wheeler parked in the site to offload the battery. That's something you have to plan ahead and make sure that you've got turning radiuses for those equipment. And just because you have a site doesn't mean you can get four batteries in there and then also be able to remove the batteries if needed once that time comes.
Thank you. We have a sort of similar question regarding lessons learned, but from a regulatory perspective. In other words, anything in the course of getting projects approved or being able to get any kind of needed permits or approvals from regulatory bodies?
Well, we have one thing that helps is that we're integrating the batteries with our own system. So that part's pretty straightforward and don't have too many issues there. And from a permitting standpoint, what we've been able to do, and this is obviously going to be different in every state or every county probably. The way that our site requirements are set up right now, we've got a lot of flexibility in siting electrical equipment, and so we haven't run into any real issues with permitting, regulatory bodies, or anything like that. It's been, for us, the one issue we had was really just a customer concern about not wanting to see the battery from their house, and so it was interesting that the customer was very very upfront with us and said, I know that you can put this battery here if you want to. there's no no regulation that would prevent you from doing it, but I don't want to have to look at it. And he managed to stir up a few of his neighbors to do the same thing, and so we were able to find a new site just down the road that was a little more accommodating.
Okay, let's talk about fire suppression. We have somebody asking what type of fire suppression systems are you requiring or purchasing with these battery systems?
We're not putting specific requirements around fire suppression. I think one of the things that I learned from Waylon is that with the lithium-ion batteries, you're probably not going to put out a fire, that it's more about just making sure that it doesn't spread. And so that's what we've tried to address, is just how, when I say we're not requiring fire suppression, the systems have got some monitoring and thermal runaway prevention, that sort of thing. But as far as spraying water on it or anything like that, we're not requiring that be installed on the batteries.
Okay. Somebody is asking, have you seen any issues with frequency or voltage control? And how long was the learning curve for your distribution operator?
Haven't seen anything related to frequency. On voltage, I'm not aware of any. Aaron, have you heard of any voltage issues?
I guess the only thing that you could point out is on a distribution feeder, if there's tap areas or no tap areas, you just have to be cognizant of what you set your step-up transformers and your output voltage for your as far as grid forming goes. But in the systems that we have currently, we haven't seen anything. We did a microgrid test with the police service center battery, and there were absolutely zero issues with voltage and frequency.
The other thing I would say, back to the question about the operator, with the first system that we put in at the airport, we spent a lot of time testing it, which both from an operator controlling it manually as well as utilizing a microgrid controller. And I think all the time we put in on that first one made the subsequent batteries a lot easier. The challenge, though, was that, as we were talking about a while ago, we had 3 different battery vendors, which meant we had 3 different processes for how you black start a battery, or even how you charge and discharge a battery for peak shaving. And so that was a little bit of a challenge, but what we were able to do was within our SCADA system, we created a display that allows the operators to see the relevant parameters about each battery all on one display, and they can initiate the charging or the discharging directly from that display. So regardless of whether the command sequence may be a little bit different, we were able to put in some automation there and make it a little more consistent even across the battery vendors. And it's kind of we looked at some DERMS applications to see whether or not there was value for us to jump right into that. And quite frankly, I think we were able to get maybe 60, 70, 80% of the benefit of a DERMS through this display creation that our SCADA engineer developed. Now, I think Aaron has pointed out to me a time or two that if we continue to grow our battery fleet, that it may get to the point where we do require a DERMS, something that gives us a little more capability in how we manage those batteries. But for the time being, we're able to do the monitoring and the control of them through a SCADA display.
Great. Well, listen, this sounds like a very successful series of projects. I wish we had more time. We do have questions we haven't gotten to, but unfortunately, we are at the top of the hour. So thanks to everybody who participated and joined us. Samantha, do you want to mention an upcoming webinar?
Sure. We do have a webinar coming up next week, also related to energy storage. We'll be talking about Clean Energy Group's Resilient Power funding programs, and I think that'll be really interesting. You can read more about that on our website, cesa.org/webinars, and I'll also send a link to that along with the follow-up materials from this webinar.
Okay. Well, thanks everybody, and we'll see you next time. Bye-bye.